Hello, my name is Georgios Giouvanis. I will present you a design space exploration in hybrid control with rapidly exploring a random tree star algorithm and combined artificial potential field methods for UAV obstacle avoidance. Uh, I will start with a small introduction, then I will show you the methodology, the experiments and the results, and the intended future work. Artificial potential field is a real-time obstacle avoidance method that aims to achieve autonomous and secure path planning. A problem that this method have is stuck in a local minimum that makes the UAV not able to reach the target. This method tries to balance two forces, the attractive and the repulsive force, where the attractive force attracts the UAV, the drone, to the goal, and the repulsive force repels the UAV from the obstacles. We combine two APF methods, one with a virtual force and one with a rotational force that helps the UAV rotate through the obstacles, avoiding making unnecessary maneuvers. Each of the of one of these force have a gain parameter that influence the intensity of the force in the total force. We use the hybrid control method that consists of three layers: the deliberative layer, where a global planner, the rapidly exploring random trees star, tries to find the optimal path. Then execution layer and the reactive control layer, where the APF method is used to avoid the new detected obstacles. The pipeline of the hybrid control is the following. We feed the algorithm with a sequence of waypoints and also with the data from the 360 degrees 2D LiDAR. We convert the laser scan data to a point cloud and the point cloud to octotrees to have a dynamically updating occupancy grid map. Then in the execution layer, we publish the waypoints, and while during the mission, if there is an obstacle newly detected in less than 3 meters, we activate the local planner that uses the APF method to avoid the new detected obstacle. Here, our experiments have been conducted in gazebo simulation environment and are to visualize the sensors. At the left, you can see RVs. The straight blue line is the line from the start to the goal if there were no obstacles. The red sphere is the closest obstacle that is detected from the UAV algorithm. And here you can see UAV avoiding obstacles while trying to reach the target and the UAV's trajectory. I will show you two scenarios where the scenario at the left, we can see that the attractive force, attractive gain is higher than the scenario at the right, but the repulsive and rotational gain is lower. That makes the UAV attracted more to the target while avoiding obstacles. So in the end, we'll we need less time, and the trajectory will be shorter. At the right, you can see that because the rotational gain is higher, the UAV rotates more through the obstacles than trying to reach the target. But in both cases, the UAV avoiding the obstacles and is reaching the target. We used uniform lighting hypercube sampling in order to create 20 scenarios with different set of these gain parameters where we saved for this for each of this set, we saved the total path length of the UAV as the result, and also the minimum distance that the UAV had from the obstacles. This is just an indicative example where the blue line represents the path if there would be no obstacles, the path of the UAV, and the red line represents the trajectory of the UAV while avoiding the obstacles. Here in these three scenarios, we can see how sensitive this method is to these parameters. In the scenario 11, because the repulsive force is repulsive gain is less than the other two, we can see that the UAV passes closer to the obstacles, while in the scenario 17, the red line, the repulsive gain is higher, so the UAV passes farther from the obstacles. And in the scenario 20, because we have less attractive gain and more repulsive and more rotational gain, makes the UAV rotate through the obstacles, so in the end we'll make a longer path. We created also a correlation matrix in order to understand the influence of each of these three parameters in the total path length and the minimum distance from the object. We see that the attractive and gain and the rotational gain is reverse proportional, both are reverse proportional to the total path length, but also to the minimum distance from the objects. That means the higher the attractive gain, the longer will be the total path length. The shorter, where the attractive gain is higher, the total path length will be shorter, but also the minimum distance from the objects will be shorter. On the other hand, when repulsive gain is higher, the total path length will be longer and the minimum distance from the obstacles will be longer also. In conclusion, using artificial potential field method, we understand that it's very sensitive to these gain parameters, but also to the velocity. We use just 2 meters per second. If the velocity will be higher, these parameters might need to be adjusted to a higher values. The correlation analysis aids to determine the optimal gain parameters and values by multiplying these gain parameters with the proportions of the correlation matrix. We can understand the influence the APF method will have in the trajectory of the UAV. Therefore, we understand that the attractive gain always should be less than the repulsive gain, and taking consideration the difference also between them, because the higher the difference will be between them, that makes the UAV navigate farther from the obstacles. Also, the influence of the rotational gain should be less than the attractive gain in order to avoid rotating through the obstacles rather than just smoothing the path. In the future work, we will do real-world experiments and evaluating them. We also use reinforcement learning to optimize these gain parameters, as this method is very sensitive to them. And also we will implement this method for autonomous underwater vehicles. Thank you for your attention.